Okay, so now let us consider a practical example. So application forecasting housing start. Figure 6.4 shows monthly data on US housing start between January 1946 to November 1994, which are seasonal because it is usually preferable to start houses in the spring, the construction, so that they are completed before winter arrive. So we will use data from January 1946 to December 1993 for estimation, and then data from January 1994 to November 1994 for our sample forecasting. So this is data. So if you inspect, so here we zoom in on the January 1990 to November 1994 to inspect for seasonal pattern. So you can see that it has seasonal variation. So the figure reveal that there is no trend. Okay, so you see that there's no trend, but it has seasonal variation. Okay, so that's it is adequate to model the series using the pure seasonal model that's given by this model or this equation. So YT, so we do have, so in this case, we include all dummies, the dummy for, so here we have monthly data, so then we need to have 12 dummies. So you have I equal to 1 up to 12. Okay, so gamma 1 D1 T plus gamma 2 D1 D2 D2 T plus gamma 3 D3 T and so on. So you estimate you get this one. So the 12 seasonal dummies account for more than a third of the variation in housing start, as R square equal to 0.38. At least some of the remaining variation is cyclical, which the model not designed to capture. Or maybe we estimate the model first. So this one. Okay, so this is the data in eViews file. So, okay, now, so originally we only have this data. So in order to estimate the model, you need to create dummy variables. So to create dummy variables, you can, so this one, dummy variable, you can see that the dummy variable for January, we assign 1 for January, 0 for other months. Only for January, we assign 1. Okay, and then for February, we do the same. Only for February, we assign 1, and then 0 for other months. So you do the same for other months. So you have D3, D4 up to D12. So if in eViews, how to create this one, this seasonal dummies, you can just go to quick. Okay, let's say maybe I just delete this one first. Okay, to show you how to create the dummy variable. So you go to quick, generate series, and then let's say you name it as D1, so equal to SEAS1. So if you have monthly data, then you put SEAS1 in bracket, then you create a variable for January. Okay, so you have quarterly data, then you put like this, then you create dummy for the first quarter. And then for, sorry, this one not D10, D1, D1. Okay, so that's how we create dummy variable in eViews. So you can do the same for D2, D3, and so on. So D2 you put so D2 equal to at SEAS in bracket 2. Okay, and then you create dummy variable, this one, the second one. All right. But if you create dummy variable like this, in order to estimate the model, remember that if you want to produce forecast later on, then you need to make sure that the assigned value, the value assigned not only for in sample, but also for out sample, that covers for the period that you want to produce forecast. Okay, otherwise you cannot, later on you won't, I mean, the what we call the eViews will not be able to produce forecast if you don't assign what we call the value for dummy variable for our sample. So it is what we call that, okay, just that one. So this one we can just estimate the model. Okay, estimate the model. If you created the dummy variable first, and then you can just put like this lah. So here start variable, and then because we want to include all dummies, do not include the intercept and C exclude the C because we want to include all dummies. So you put D1, D2, D3, D4, D5, D6, 7, 8, 9, 10, and then D11, and then D12. Okay, so here, let's say you put C, what happened? Okay, so you say that we do have perfect collinearity, so perfect multi-collinearity problem. So because we include all dummies together with the intercept, so we cannot, because remember the explanation I gave you just now that your X matrix, you have all the first column all equal to 1, but then you include all dummies so that the sum of all dummies are equal to 1. The sum of all dummies is equal to 1. Okay, so you exclude C, include all dummies, then you get this one. Okay, so each of these represent estimate of seasonal factor. Okay, seasonal factor for each of the months for January, February, March, April, and so on. So alternatively, if you don't want to create season dummy first, when you estimate the model, you can just use this command. So I actually encourage you to use this one because you don't have the problems of what we call that. Because this one, if you generate the series, the dummy variable, okay, it will only create a sign value for in sample. For the sample, this one it does not. It will not assign value for the range outside the sample. So later on, if you want to produce forecast for the period outside the sample, then EViews will not be able to compute forecast because there's no values for the dummy variable for the outsample period. So so meaning that when you create or generate the series, the dummy variable, you need to change this one. The sample to cover the outsample period first, and then after you what we call that, you have all the dummies, then you change the sample range to cover for in sample only. Or alternatively, you just use this one. When you estimate, you just use this command. You put what we call the expand, and then you put you have monthly data, you put months, and then it will create what we call that in the model. It will add all the dummy variables. Okay, so so this one we include all dummies without C. Okay, if you put C, then you have the problems of perfect multi-collinearity. So we get the same what we call that result of estimation. Okay, so this one seasonal factor for the January, February, and so on. So so it is better to use this one, okay, because you don't have the problems of if let's say I mean just now if you create a variable, then it only assign value for in sample, then you cannot produce forecast for our sample. So you don't have that problem if you use this command. Okay. Okay, so this is the result. So we have the R square. Okay, just R square. So R square only 0.38, 3780. Okay. Okay, so this is the result, and then notice that it has a very low Watson statistic. Okay, you see the expand. So in this case, just now I explained to you that the R square just 0.383780. And then the Watson 0.1544140. Okay, so it has very low Watson, less than 1. So if you refer to the additional, or we call the explanation given here, so the Watson statistic test for correlation over time called serial correlation in regression disturbances. The Watson test works within the context of the regression model. So basically, remember that one of the assumption for the error term in a regression model that it must be random and independent each other. But if there is a correlation between current error and the previous error, so we do have the problems of the first order autocorrelation. So the regression disturbance is really correlated when the value of this coefficient, okay, not equal to 0. So that the Beam-Watson statistic is given by this formula. So the Beam-Watson takes values in the interval 0 to 4, and if all is well, the Beam-Watson should be around 2. So if the Beam-Watson is substantially less than 2, there is evidence of positive autocorrelation. If the Beam-Watson is substantially greater than 2, there is evidence of negative autocorrelation. So just now, for our example, then the Beam-Watson is substantially less than 2. Okay, so it is close to 0, so that it indicates the presence of positive autocorrelation. Okay, so this one substantially less than 2, so the evidence of positive autocorrelation. So basically, a good model without autocorrelation problem in the error term, that the value of the Beam-Watson must be around 2. Okay. So the residual plot in figure 6.6 makes clear the trend and limitation of the model. There is nothing in the model other than deterministic seasonal pattern every year. So it picks up a lot of the variation in housing start, but it however does not pick up all the of the variation as evident by the serial correlation that is apparent in the residual. Okay, so you check this one. And then you can see this one. So if you, okay, so if you go back to the eViews data, this one you estimate. So you go to view and then you go to actual fitted residual table, you see the value of the actual fitted residual. And then if you go to actual fitted residual graph, you can see. So this one, residual, it is obvious that residual is not what we call that random. It's not random. Okay, so it shows the presence of positive autocorrelation. All right, so the estimated Zener factors are just the 12 estimated coefficient on the Zener dummies as given in the next figure. Okay, this one. So the value given, this one represent the value of seasonal factor. So this one, the first month, January, February, and so on. So the seasonal effects are very low in January and February, and then rise quickly and peak in May, after which they decline at first slowly and then abruptly in November and December. This one. Okay. So figure 6.9 give the history of housing start through 1993 together with the out of sample point and 95% interval extrapolation forecast for the first 11 months of 1994. Forecast look reasonable as the model eventually done a good job of capturing the seasonal pattern. The forecast intervals are quite wide, reflecting the fact that the seasonal effect captured by the forecasting model are responsible for only about a third of the variation in the variable being forecast. The forecasts appear highly accurate as the realization and forecast are quite close. In addition, the realization is everywhere well within the 95% interval. So this one. So how to predict forecast in the views? So just now we estimate our model using data from January 1946 to, okay, so to December 1994. Okay, and then we want to produce forecast for the next 11 months. So from January 1994 to November 1994. Okay. So to produce forecast, you just go to, after you estimate this one, you go to forecast and then name the forecast series. And then if you want to compute forecast interval, then you need to save this one. So let's say you put SE, and then you need to change the range forecast sample. So it is 1994, January to 1994, November, and then okay. Okay, why November? Because I think the data we have up to November only. Okay, only up to November 1994. Okay, so that because we have the value of the observed value of the series for the 11 months, and then we just produce forecast for the 11 months, then if used, will compute the accuracy measures for us, the RMSE, MAPE, and so on. If we don't have the actual value for our sample, then if used will not give us this one. Okay, the accuracy measures. So this is our point forecast for the 11 months, and then the 95% forecast interval. So 95% forecast interval, just the point forecast, okay, which is given here. Our point forecast is given, so for the 11 months. So this one. So all the other value are the actual value, okay, in sample, the actual value of the series. It's one of our forecast values. So the forecast value plus minus 1.96 times the SE. Okay, forecast and error. This one forecast and error. So this one plus minus 1.96 times this one give us what we call a 95% forecast interval. So if use here, so if use is simply use this one plus minus 2 times SE, okay, instead of 1.96. But it's more accurate to you. I mean, if the error terms normally distributed, then it's more accurate to use 1.96. Okay, but it also we call that we also can just simply use what we call that this one 1 plus minus 2 times SE. I mean, not much different. 1.96 and 2 times SE. Okay, so okay, so this is our estimated model. Okay, so we produce forecast just now, and okay, let's say we want to estimate the model using the second approach, meaning that we add the intercept, but we exclude one of the dummy. So maybe we save this one as equation 1 first. Okay, so all right, so this is the first model. If you compare, alternatively, we can just estimate the model. Okay, by having n intercept in the model. Okay, I will start. And then we have intercept in the model, but we cannot include all dummies. So we exclude one of the dummies. So let's say we exclude the first one. So in this case, we exclude the D1. So you just put like this one, months. So remember this one, if you have monthly data, you put at months, but you have quarterly data, you put at quarter. Okay. So in this case, we want to, okay, you see, you have the C and this one, and then we do have the problems of perfect collinearity. So in this case, you need to drop one of the dummy. So let's say we drop the dummy variable for January. So drop first, use drop first. Okay, so you can see that so this one, because we exclude D1, so that the C represent seasonal factor or intercept for the first for the January. So we get exactly the same. All right, but the coefficient for the seasonal dummies represent additional intercept in addition to the value given for the omitted season. This one for January. So this one, in addition to January, February has additional value of intercept equal to 3. So that this 86 plus 5, 86.5 plus 3, it is equal to 89. Okay. For the March, okay, in addition to this value, March has additional value of intercept, 36.37. So this plus this is equal to 122.833. Okay, that's how we interpret this one. If you this model, then it gives you estimate of the additional, okay, additional amount of intercept relative, or we call that as compared to the one that represented by the omitted season. Okay, the omitted variable pseudonymy. That you drop first, let's say you drop last. So you only have two options, drop first or drop last. If you drop last, then it will drop the last one, which is December. Okay, so that you'll see the intercept represent intercept for the one that excluded, that is for December. So you see that you have exactly the same value, this one and this one. Okay, and then this one represent the additional, okay, additional or less value of the intercept as compared to the value for the one, the reference category. So this reference category is December. So for January, it has a negative 5.6 lower value of intercept as compared to December. Okay, so that if you this one minus this, you get 86.5. All right, so that's how we interpret what we call that. If you use this, the first model, or use this one. All right, so doesn't matter which one, which model you use, that the forecast value just the same. So you produce the same value of forecast. Okay, but just remember that the way we interpret the coefficient, estimated coefficient, different. So not the same, because for example, in this one, it represent each of these, it represent additional. Okay, as compared to the what we call that the reference category. But this one, each of these represent the direct estimate of the seasonal factor for each of the different months.